Hello everyone. Class 2 dimensional analysis. Let us discuss in class 2 about similitude, types of similitude and dimensionless numbers. Before going to similitude, let us discuss about model analysis. So what is model analysis? So predicting the performance of hydraulic structures that includes dams, spillways, etc. or hydraulic machines such as turbines, pumps, etc. Before actually constructing or manufacturing, the models of the structures or machines are made and tests are performed on them to obtain the desired information. So this is applicable, model analysis is applicable for hydraulic structures or some hydraulic machines, namely turbines, that's a work producing device, pumps, that is a work absorbing device. So before actually constructing or manufacturing them, the models of the machines or components are made and tests are performed on them to obtain the performance characteristic or to obtain desired information. So the model is the small scale replica of the actual structure or machine. So it is model, whatever the model we are going to construct, this is of small scale replica. Replica means it should be similar to the machine component of the structure or machine. The actual structure or machine is called prototype. Here actual structure or machine component, that is called as a prototype. So next, it is not necessary that the models should be smaller than prototypes. So in all the cases it may not be like the small scale, the model should be small scale the replica of the actual component. It may be a larger scale replica of the component. So for example, in some cases the models may be larger than the prototype. For example, the model of the tool, that is the whatever the tool you are going to use for lathe machine and all. So model of the tool, electronic chips, and it may be in case of engine parts. So how to construct the model, it should be of dimension larger than that of the actual component or actual tool. So the study of models of actual machine is called model analysis. So this is whatever the model you are going to construct or manufacture, whatever the information you are going to get from the model by studying them, that is called as model analysis. Model analysis is actually an experimental method of finding solutions of complex flow problems. So whenever you encounter some complex problems related to flow problem, so you can go for experimental method. Experimental method in the sense, here we are going for construction or manufacturing of small scale or large scale replica of actual component. So whatever the result or experiment you are going to perform on that model, that is similar to the experimentation on actual model, that is called as prototype. So next, exact analytical solutions are possible only for limited number of flow problems. Here they explain why you are going for experimentation. So analytical method or theoretical method is possible only limited number of problems. You cannot perform analytical or theoretical calculation for all the problems. So like in case of complex flow problems, you should go for experimentation. So that is a use of model analysis. Next, the following are the advantages of model analysis. The first point, the performance of hydraulic structure, that is dams or spillways, or hydraulic machines, turbines or pumps, can be easily predicted in advance from its model. So by constructing or manufacturing the model, you can understand the performance characteristic of or performance of hydraulic structure or hydraulic machine. It reduces unnecessary expenditure of actual structure till most suitable design is obtained. So you can by constructing the model, you can reduce the cost or expenditure involved in maintaining actual structure or actual design. So it can be used like you can modify the design until you are going to get suitable design. So with the help of dimensional analysis, a relationship between variables influencing a flow problem in terms of dimensionless parameters is obtained. This relationship helps in conducting tests on the model. So with the help of dimensional analysis, anyhow I am going to discuss about Buckingham Pi theorem and Rayleigh method. There is a dimensional analysis method. So by using that, you can establish relationship between variables, for example density, dynamic viscosity, or length, diameter of the component. Next, the merits of alternative design can be predicted with the help of design model testing. The most economical and safe design may be finally adapted. By going for model analysis, you can construct models of different shape and different dimensions. So you can adapt finally a safe design or optimized design you can adapt for final structure or final component. The test performed on the models can be utilized for obtaining in advance useful information about the performance of the prototypes only if a complete similarity exists between the model and prototype. So the test whatever you're going to perform on the models can be utilized for obtaining useful information about the performance of the prototype. If the prototype and models are of same shape and it has some scale ratio, then you can utilize that information for constructing or manufacturing of actual model, or that is called as prototype. Next, applications of model analysis. Some of the fields where model analysis is used are as follows. Especially the model analysis or construction or manufacturing of the models that is applicable for following points or following applications. So structures like dams, spillways or canals, that is hydraulic structures. Then hydraulic machines like turbines, pumps, compressors. As we all know, turbines are work producing device. For example, steam turbine where steam is used as a working fluid. Then pumps, there's a work absorbing device that is used for pumping of water or any fluid. Then compressors, to get desired pressure ratio you can go for compressors. So design of ships and submarines, it is also used in ships and submarines. Then design of aeroplanes, as a most important application of model analysis is in the field of aeroplanes, rockets and helicopters, so where a small or scaled down model of the actual prototype is made. So next, in the field of automobile engineering, you can apply model analysis in the field of automobile. Next, similitude and types of similitude or similarities is a very important question for 10 marks. There are three types of similitude: geometric similitude, kinematic similitude and dynamic similitude. This is very important. So 10 marks or 12 marks you can expect. So first let us discuss what is similitude. Similitude is defined as similarity between model and its prototype in every respect. So it is a similarity between model and its prototype. Prototype means actual structure. So it means that model and prototype have similar properties, or model and prototypes are completely similar. So when you are going for construction of model, it should have some properties or some dimensions similar to the or shapes that is similar to the prototype. So three types of similarities must exist between model and prototype. That is very important. Three types of similarity should match with respect to model and prototype. First one is geometric similarity. Second one is kinematic similarity. Third one is dynamic similarity. Now first let's go for geometric similarity. So as the name itself indicates, there is a similarity with respect to shape and size. So geometric similarity is said to be exist between the model and the prototype, that is the actual model, if the ratio of corresponding linear dimension in the model and prototype are equal. So if the ratio of corresponding linear dimension, that may be related to length, breadth, if those are same, then it is called as the model and prototype said to have geometric similarity. For example, let us consider the case below. Let LM, there is a length of model. M stands for model, LM length of model, BM breadth of model, DM diameter of model, and AM area of model, and VM volume of model, and LP, BP, DP, AP and VP corresponding values for prototype. Now for the geometric similarity between model and prototype, we must have the relation. This linear ratio of linear dimension should be same for prototype as well as model. So let's first consider length as a linear dimension, that is LP divided by LM, that should be constant, or that is equal to BP by BM, or that is equal to DP by DM. So ratio of length of prototype and model, that is equal to ratio of breadth of prototype and model, and that is equal to ratio of diameter of prototype and model, that we are going to consider as LR, where LR is called as scale ratio, that is with respect to model. So for areas and volumes ratio, the relation should be as given below, that is AP divided by AM, that is the area of the prototype to area of model, that is equal to, as we all know, area equal to length into breadth for a rectangular cross section. So that is equal to AP equal to LP into BP and AM equal to LM into BM. So ratio becomes LP into BP divided by LM into BM. But we all know LP divided by LM is LR. Similarly, BP divided by BM is LR. So that becomes LR into LR, that is equal to LR square, where LR is scale ratio. And volume, we all know the volume of a prototype to volume of model, that is equal to, that is the unit is if you are going to consider it as a square cross section, then it is a cube. Volume becomes a cube. So LP divided by LM to the power 3, that is equal to BP divided by BM to the power 3, that is equal to DP by DM to the power 3. That is actually for a volume linear dimension of length and linear dimension of breadth and linear dimension of diameter that is considered. So as we all know, LP divided by LM, that is LR to the power 3, and BP divided by BM, that is LR cube. DP by DM, that is again LR cube. So this is a geometric similarity. This is with respect to shape and size. So that otherwise it is with respect to linear dimension like length, breadth and diameter. So area ratio and as well as volume ratio can be considered from using the length, breadth and diameter ratio or scale ratio. Then kinematic similarity, as the name itself indicates, it is with respect to motion between model and prototype. So kinematic similarity means similarity of motion between model and prototype. So the kinematic similarity is said to exist between the model and the prototype if the ratios of velocity and acceleration at the corresponding point in the model and corresponding points in the prototype are the same. So as we all know, for motion the two flow properties are velocity and acceleration, important flow properties. So that should be considered. So it is said to be exist between model and prototype if velocity and acceleration at corresponding point in prototype and corresponding point in model is same. Next, since velocity and acceleration are vector quantities. What is vector quantity? Vector quantity means it has magnitude as well as direction. So it is direction dependent parameter, velocity and acceleration. Hence, not only the ratio of magnitude of velocity and acceleration at the corresponding points in the model and prototype should be same, but also direction of velocity and acceleration at the corresponding points in the model and prototype should be parallel or should be same. So there is a case, velocity and acceleration are vector quantities. So not only the magnitude, that is a value, should be same. Not only the magnitude but also the directions of velocity and acceleration should be parallel, should be same for model and prototype. So that is with respect to kinematic similarity. So we can consider a case below. Let VP1, that is velocity of prototype at point 1, velocity of fluid at point 1 in prototype, then VP2, velocity of fluid at point 2 in prototype, P stands for prototype, then AP1, acceleration of fluid at 1 in prototype, and AP2, acceleration of fluid at point 2 in prototype. Similarly, VM1, VM2, AM1, AM2, M stands for model, this is the actual structure. That is the corresponding values at the corresponding points of fluid velocity and acceleration in the model, that is applicable for model. So let us consider for the kinematic similarity, we must have velocities at the corresponding point in prototype and model should be same. That is VP1 divided by VM1 with respect to point 1, that is equal to VP2 divided by VM2, that is equal to VR, where VR is called velocity ratio. So when you are going to consider 2 points, for one point is with respect to prototype and model, that is VP1 divided by VM1, that should be equal to VR, or with respect to point 2, VP2 divided by VM2, that is again called as VR, that is a velocity ratio. Similarly, you can apply same concept for acceleration. We must have AP1 divided by AM1, that is acceleration at point 1 in a prototype, to acceleration in model at point 1, that should be equal to acceleration ratio AR. So AP2 divided by AM2, that is acceleration at point 2 in prototype, is to acceleration at point 2 in model should be equal to acceleration ratio, or that is AR. So that's the acceleration ratio. But here you have to remember, here in kinematic similarity, not only the magnitude of velocity and acceleration, but also the direction of velocity and acceleration should be parallel or same, because velocity and acceleration are vector quantities. Next, dynamic similarity. There's a last case of similarity or similitude. So dynamic similarity means the similarity of forces between the model and prototype. So it is with respect to first one, that is geometric similarity, that is with respect to shape and size. So linear dimensions are considered length, breadth and diameter. From that you can you consider area ratio and volume ratio. For geometric kinematic similarities, the motion is the parameter, there's a velocity and acceleration. Now last one, dynamic similarity, for that the force is considered. So dynamic similarity is said to exist between model and the prototype if the ratios of corresponding forces acting at corresponding points are equal. So also direction of the corresponding forces at the corresponding point should be same, because force is also vector quantity. So the ratios of corresponding forces that is acting in prototype and model should be same or equal, that is equal to also also direction of corresponding forces at the corresponding point should be same. So let us consider the case below. Let FIP, that is Fi stands for inertia force at a point in a prototype, then FVP, that is viscous force, V stands for viscous, P for prototype, viscous force at the point in a prototype. So FGP, that is a gravity force at a point in a prototype. Similarly FIM, FEM and FGM, that's the corresponding values of force at the corresponding point in the model. So M stands for model. So ratios of corresponding forces acting at the corresponding points are equal. There's a condition for dynamic similarity. Force is considered. There's again vector quantity. So force direction should be same or parallel. So then for dynamic similarity we have FIP divided by FIM. That's a inertia force at a point in a prototype to inertia force at a point in model, that should be equal to viscous force at a point in prototype to viscous force at a point in model, that is equal to gravity force at a point in a prototype to gravity force at a point in model should be equal to FR. That is, FR is called as force ratio, because we are considering here force. So also directions of corresponding forces at the corresponding point in the model and prototype should be same, because force is a vector quantity. Okay, next, types of forces acting in moving fluid. That's with respect to moving fluid, not stationary fluid. For the flow problems, the forces acting on fluid mass may be any one or combination of several of the following given. So that may be like one force acting on fluid in motion, or the combination of following forces. First force is inertia force, that is Fi, inertia force, I for inertia. Viscous force, that is Fe, V for viscous. Gravity force, that is Fg, G for gravity. Pressure force, that is Fp, that is P for pressure. Surface tension force, that is Fs, S for surface tension. And elastic force, Fe, E for elastic force. Okay. Now let us consider one by one. First one is inertia force. As we all know, inertia force is due to motion, due to the mass of the fluid element. So it is equal to inertia force from Newton's second law, F equal to ma. So that is the inertia force, because it involves mass as a parameter. So it is equal to product of mass and acceleration of flowing fluid and acts in the direction opposite to the direction of acceleration. It always exists in the fluid flow problems. So it is always existing in fluid flow problems. Inertia force given by from Newton's second law, mass into acceleration of the flowing fluid, and it is direction of inertia force is exactly opposite to the direction of acceleration. So it is represented by Fi. You have to remember Fi equal to me. Next, viscous force Fe. It is equal to product of shear stress. We already studied about shear stress, that is tau, in first module, due to viscosity and surface area of the flow. It is present in fluid flow problems where viscosity is having an important role to play. So wherever in problems viscosity is important, then you have to consider viscous force, that is the Fe. That's a predominant force. So viscous force, it is given by, as we all know, tau equal to F by A. Now in order to get force, I have to just cross multiply tau into A, where A is surface area. So viscosity force F equal to shear stress into area. So how to get shear stress? From okay, about that thing I'll discuss later. So viscous force F equal to shear stress into area. Next, gravity force Fg. So as we all know, gravity force, that is with respect to weight of the component, that is given by W equal to mg, or Fg equal to mg. So it is equal to product of mass and acceleration due to gravity of the flowing fluid. So inertia force, that is due to mass and actually acceleration, but here this is with respect to weight, gravity. So to consider acceleration due to gravity, that is 9.81 meter per second square. So Fg equal to mass into acceleration due to gravity. There is a mathematical expression for gravity force. Next, pressure force. Again, you know, pressure equal to force by area, because unit of pressure is Newton per meter square. Newton is unit of force. In order to get force, you have to multiply pressure by area. So it is equal to product of pressure intensity and cross-sectional area of the flowing fluid. It is present in case of pipe flow. So pressure force, almost it exists in pipe flow or flow through a pipe. So it is given by intensity of pressure into cross-sectional area, that is P into A. P for small letter P for pressure, A is a cross-sectional area. Next, surface tension force Fs. As we all know, the surface tension is a force acting per unit length. Unit is Newton per meter. So surface tension equal to force by length. So in order to get force, surface tension force, you have to multiply surface tension, that is sigma, into length. So you are going to get surface tension force. It is equal to product of surface tension and length of surface of the flowing fluid. So Fs equal to surface tension force, that is equal to surface tension per unit length, that is sigma, into length. When you are going to multiply Newton per meter by length, then you are going to get Newton, that's a surface tension force, sigma into L. Then last one is elastic force. It is equal to product of elastic stress and area of flowing fluid. So elastic force, it is with respect to elastic stress. As we all know, stress equal to force by area, shear stress similar to shear stress. So in order to get elastic force, elastic stress into area. So elastic stress in case of fluid, that is a bulk modulus K into A. Next, for a flowing fluid, the above mentioned forces may not always be present. Also, the forces which present in a fluid flow problem are not of equal magnitude. There are always one or two forces which dominate the other force. These dominating forces govern the flow of fluid. Okay, so out of 6 forces, there may be one or two forces that may act on the fluid element, and one or two forces that may be predominating others. Like for example, in case of viscous flow problems, viscosity force is predominant, and in case of gravity problem, gravitational force, that is W equal to mg, that is a predominant factor. So that's what. Next, dimensionless numbers, very important concept. Dimensionless numbers, to remember this thing, similitude and dimensionless numbers, very important concept in 4th module. Okay, let us discuss about dimensionless numbers. Dimensionless numbers, as we all know, dimensionless, it has no dimension. If it is not having dimension, means it has no unit. So dimensionless numbers are those numbers which are obtained by dividing inertia force by viscous force, or gravity force, or pressure force, or surface tension force, or elastic force. As this is a ratio of one force to another force, it will be a dimensionless number. Here they are explaining about reason for dimensionless, or no reason for it is not having unit, just because it is a ratio of two forces. When the unit of force is Newton by Newton, that becomes dimensionless. These dimensionless numbers are also called non-dimensional parameters. Instead of otherwise you can call these dimensionless numbers as non-dimensional parameters. So I'll explain one by one. Now let us go for, there are like the following are important dimensionless numbers. First one is a Reynolds number, second one is Freud's number, third one is Euler's number, fourth one is Weber's number, and fifth one is Mach's number. So Reynolds number, it is defined as ratio of inertia force of flowing fluid and the viscous force of the fluid. So you have to remember Re, Reynolds number is represented by Re, that is equal to Fi divided by Fe. So Fi is the inertia force. I already explained about inertia force, that is mass into acceleration, and Fe, that is a viscous force, that is a shear stress, tau into area. So expression for Reynolds number is obtained as follows. Inertia force Fi, that is given by definition of inertia force as mass into acceleration of flowing fluid. So mass, if you know the density, that is rho equal to m by v, you can get mass by cross multiplying density by volume. So mass becomes rho into volume. Acceleration, as we all know, rate of change of velocity is acceleration. So velocity by time, or velocity has a unit meter per second. When you are going to divide by again time, that is second, it becomes meter per second square. There is a unit of acceleration. So rho into volume into velocity divided by time. So just rearrange rho into volume divided by time into velocity. So as we all know, volume divided by time, that is meter cube per second. That is a unit of cube. From continuity equation for incompressible fluid, Q equal to AV. So you can replace volume by time as AV. That's the area into velocity. So that is equal to rho into AV into V. So since volume per second, that's what Q equal to area into velocity from continuity equation for incompressible fluid. So AV into V. So that becomes rho A V square. This is very important. I already told about this thing in Mach number. So that is equal to rho A V square. Now get expression for Fe. This is a viscous force. Fe equal to shear stress into area. Shear stress is tau into area. That's the surface area. So but Newton's law from Newtonian law, we have tau equal to mu into du by dy. Mu is dynamic viscosity, du is change of velocity, dy is there's a gradient, distance gradient, or dy. A velocity gradient is given by du by dy, or dy is the distance. So mu into du by dy, but force equal to tau into area. That is with respect to viscous force. Now tau into area, you can replace tau by mu into du by dy. So it becomes mu into du by dy into area. But for linear profile, we know du by dy equal to v by L. So you can just du is v minus 0, dy is L minus 0. So that becomes v by L, mu into v by L into area. But by definition of Reynolds number, we have Reynolds number equal to Fi divided by Fv. So that is equal to rho A V square divided by mu into v divided by L into area. So just cross, you can cancel a term there because it's a common numerator and denominator. So take your L to the numerator, that is 1 by L, that becomes L. So rho VL divided by mu. Otherwise you can mu divided by rho, that is kinematic viscosity. So dynamic ratio of dynamic viscosity to density. So rho R equal to V into L divided by mu divided by rho. So that is equal to V into L divided by mu. So since mu divided by rho equal to kinematic viscosity, that is nu. So in case of pipe flow, the linear dimension L is taken as diameter. So for a pipe flow or flow through a pipe, you have to consider, instead of length, you have to consider diameter. So you can replace L by D. So Reynolds number becomes R equal to rho Vd divided by mu, or V into D divided by mu, because mu by rho is kinematic viscosity, that is nu. Next, Froude's number. The Froude's number is defined as the square root of ratio of inertia force of the flowing fluid to gravity force. Mathematically, it is expressed as Fe equal to square root of Fi divided by Fg. That's the inertia force to gravity force. Where Fi, I already discussed about the derivation of Fi. That is equal to rho A V square in Reynolds number, and Fg, there is a force due to gravity. So gravitational force comes into picture when there is a weight parameter, that is W equal to mg. So mass into acceleration due to gravity, g for acceleration due to gravity. So mass you have to replace by density into volume. So this is because rho equal to mass by volume into g. So it becomes rho into A into L, volume is A into L, area into length, into g. So rho A L G. So therefore Fe equal to square root of Fi divided by Fg, that is equal to square root of rho A V square divided by rho A L into G. So equal to square root of V square divided by L into G. So square root of V square is V divided by square root of Lg. That's length into acceleration due to gravity, and V is the velocity. So this is also very important. Next, Euler's number. It is defined as square root of ratio of inertia force of a flowing fluid to pressure force. Mathematically, it is expressed as EU equal to square root of Fi divided by Fp, where Fp is the intensity of pressure. So intensity of pressure into area. So there is a pressure force, pressure into area. From pressure you have Fp equal to F by A. So in order to get pressure force, you have to just multiply pressure by cross-sectional area P into A. So and Fi equal to rho A V square from Reynolds number. I already derived that thing. So U equal to square root of Fi divided by Fp, that is equal to square root of rho A V square divided by Pa. So that is equal to, you can cancel their A term. So that is equal to square root of rho A V square divided by Pa equal to square root of V square. You can take rho to the denominator, that becomes that time P by rho. So but P by rho, you can take the square root of V square is V, so it becomes V divided by square root of P by rho. Next, Weber's number. It is defined as square root of ratio of inertia force of a flowing fluid to a surface tension force. Mathematically, it is expressed as We equal to square root of Fi divided by Fs, where Fi is inertia force, that is given by rho A V square, and Fs equal to surface tension force. Surface tension force, so unit of surface tension is Newton per meter. In order to get force, you have to multiply surface tension by length. So then you can cancel meter. So Newton per meter into meter, that becomes Newton. So surface tension force sigma into L. So We equal to square root of Fi divided by Fs, so that is equal to square root of rho A V square divided by sigma into L, that is equal to square root of sigma into L square into V square divided by sigma into L, because there is no A term in denominator. So in place of A, you can write area. If you consider cross-sectional area as square cross-section, then area becomes length square, so or side square. So L square equal to A, that is equal to area. So you can cancel L term there. So that becomes, that is equal to square root of sigma into L into V square divided by sigma upon cancelling one L term. So that is equal to square root of V square divided by sigma divided by rho L. So that is equal to taking square root of V square, that becomes V, that is equal to V divided by square root of sigma divided by rho L. So that is with respect to Weber's number. Next, last one, Mach number. I already discussed about Mach number in fifth model is a compressible flow. So Mach's number is defined as the square root of ratio of inertia force of a flowing fluid to elastic force. Mathematically, it is defined as M equal to square root of inertia force divided by elastic force. So that is equal to square root of Fi divided by Fe, where Fi equal to inertia force, that is equal to rho A V square, and Fe equal to elastic force. So elastic force, in order to get elastic force, you have to multiply elastic stress by area. Elastic stress is bulk modulus here, K into A. So therefore M equal to square root of Fi divided by Fe, that is equal to, upon substitution, square root of sigma rho A V square divided by Ka, that is equal to square root of V square divided by K by rho. But from derivation of velocity of sound, we have C equal to square root of dP divided by d rho, that is equal to K by rho, that is square root of K by rho, because it is in terms of bulk modulus. So that the expression becomes M equal to V divided by K by square root of K by rho. So but square root of K by rho equal to C, as I already told, from the derivation of velocity of sound, C equal to square root of dP divided by d rho, that is equal to square root of K by rho. So that is C, velocity of sound in the fluid. Therefore M equal to V by C, that's the velocity of flowing fluid to, or velocity of the projectile to velocity of disturbance or pressure wave, that is equal to V by C. So this is with respect to dimensionless numbers, very important concept, dimensionless numbers and similitude, types of similitude, geometric, kinematic and dynamic similarity, and 6 dimensionless numbers, that is very important from examination point of view. So thank you.